And we're going to do this. So here's our topic, unsupervised learning measures. We really don't have, what we're talking about today is a measure, it's not a metric. And we'll quantify what that is, just not a full distance metric. And we're going to exploit the concept of independent component analysis and what it means. So we want to walk through the assumptions piece by piece. Hopefully this will help if you already read the last parts of chapter 3. So we're talking about some signal. We say m-dimensional signal. So mathematically this belongs to Rm. It's a random variable, random vector. Without any loss of generality, we assume it has zero mean. If it's not, we are expected to compute the mean and take it out. So we're dealing with things zero mean. We're going to look at the simple step of just multiplying the signal by a matrix, transform it to another. And this matrix could be a first layer, linear layer, and also is going to serve as transforming to a new representation of the signal in a new coordinate. So we're looking at the simplest possible transformation, a linear transformation. We know at the core of the building blocks of neural networks, we have linear transformation plus a bias, which is obviously still a linear transformation. And we add nonlinearity, and we have this module, we just keep repeating it. So the core is really a linear transformation, which transforms the system from one representation to another representation. And so this is a matrix, and for every signal at the so-called output, in this case, y, it really multiplies this row, so the row, the jth row of this matrix times the signal. So it's really projecting the signal on a matrix to have a new representation. Okay? This is a scalar output, and this W is really the row of this capital W matrix. To make things simple for ourselves, let's say that the output dimension is the same as the input dimension. So therefore, we're dealing with transformations that are symmetric. It's more complicated if it's not the same size, but the concepts that we're going to build right now, they benefit from having this simplicity. Okay. So that's the transformation that we have. And the concept of independent component analysis of random variables focuses on the density, if the variables are continuous random variables, or the distribution if they're discrete. So here, we're going to assume that these variables come from a continuous variable family, and we're going to focus on the densities. By definition, independence, statistical independence, means that if you have a vector y, which we're interested in at the output, this is going to have a probability called the joint probability density. And each one of the components is going to have its own probability density called the marginal probability density. And the product of the marginal is always greater than or equal to the joint density of the whole vector. And it becomes independent, the signals, the random variable components become statistically independent if you achieve equality. Just a definition. Okay? So once we have probabilities, there's also the concept of information. To be precise, Shannon information. And information is really a play on the concept of uncertainty. So information is really measuring the amount of uncertainty or surprise if an event takes place. There are technical distinction between these words, but for our purposes now, we're going to view information as equivalent to uncertainty, measuring uncertainty. So if you have a density, P sub y of this output that you're looking at, And the information is going to be defined as another random variable, which is here. It's going to be the negative. This log or natural log is the same. We're only using natural log. So sometimes I write it log, sometimes ln. They're both, we mean the same. We mean natural log. So negative of natural log of the density. Keep in mind that density is always, the value of a density at any value here is going to be between 0 and 1, bounded by 1, right? So the log, you take the log, so that's going to be a quantity. When the probability density equals 1, which for density it never will, this log is going to be 0. If it's smaller, this negative log is going to be large. So if the density is very small, you have a huge number of information. If an event has a small probability of taking place, and it happens, you'll be totally surprised, okay? And you will gain the maximum information at that point. If an event has a probability 1, you're not surprised, it's certainty. And when it takes the information you gain from an event probability 1 is negligible or 0. Okay? So this is just how this concept is. All it is just you're defining a new variable, which is a random variable, which is quantified as such. And then if you take the mean, so this is a random variable, take the mean of this new defined random variable called info of y, which is the expected value. Because your mean, you're dealing with statistical random variables, the mean is the expected value of this quantity, is referred to as the entropy or the uncertainty. It takes the average information. Okay, so we define a variable that's information, then the average information. This stuff is in chapter 3. I assigned it last time verbally to you to read it. Okay? And if you have any questions, this is your chance. Okay? So now there's the concept of mutual information. And mutual information, if you have this vector y, we have n components in this right up here, and you have the joint density, and you have the marginal product of a marginal density, and you take the ratio log, natural log of this one here, okay? And this whole thing is your random variable, and you have the expected value of this one here. So when you say expected value, you have to decide which of these densities you're going to use. You always, by convention, use the one on top, which is p sub y, which is the joint. So that's the definition of mutual information. What's the mutual information among the components of this vector y? Okay? So this mutual information we'll see below that it's really similar to, it's in fact an application of the Kullback-Leibler divergence, because it measures the proximity between this function of y, which is density, joint probability density, and between the product of the marginals. And when these guys are equal, which then you would achieve independence, statistical independence, then this quantity will be 0. And it so happens this measure, the minimum is 0. It can only be non-negative. Any other, if this is some other quantity that are not equal, the result that this whole expression will be non-negative, away from 0. It's never be negative by definition. So we define all these things here, and I can take this one, you can just write it by taking the properties of the natural log, and you just split it this way, noting that the expected value operator is a linear operator, so you can pass it through easily. You can pass it through the summation. The linear operator is just a mapping that's linear. And then when you take the expected value of this whole thing, remember I said we're using the density, which is the joint, but when you define the joint for each one, there's a technical issue here that this becomes exactly the expected value using this marginal, okay? It's a sidebar technical issue that this carries over, and then the expected value of the natural log of the joint, which is the entropy of the whole vector, is going to equal to, you have a negative sign here, the expected value of the marginal, and we can write, as we define this one to be H, which is the entropy, define it upstairs. Then you have H of the whole vector Y, HI for each one of the marginal outputs, Y, and you have the summation. So it really becomes a difference between two quantities called entropies, which is a measure of uncertainty. Entropy is the mean information, the mean or average information. Okay? So it's really the difference between the entropy of the whole vector vis-a-vis the sum of the entropies of the marginal components. Okay? So now this mutual information is a measure, a guidance that we can use to optimize or minimize, okay, to achieve, in this case, what? Independence among the outputs. So from this example, when I have a linear mapping, I look at the output. If I develop a criterion to change the matrix, W, according to minimizing this mutual information, I'm going to, from any signal I have, I'm going to output signals Y, which outputs marginal signals that are statistically independent. So you can do this one by this transformation. In other words, you can find the weight matrix that will render from an input signal outputs that are statistically independent. Okay? Because we achieve a measure if we can find a way how to use this one here. So far I'm documenting all the information. And again, it's your chance to ask any questions. If you read something that's not clear in the chapter 3, I'm summarizing things equivalent to the stuff over there. And I'll give you the chance to ask any questions about it. So this mutual information is really a special case of using the Kullback-Leibel divergence measure, which is, in its general definition, it's the ratio between densities, any arbitrary densities. In this special case, we looked at the joint density vis-a-vis the product of the marginals. That's a special case of that signal. But for any random variable Y, you can say, I'm going to have one density for this Y and another density, and I have a measure of proximity between these densities. Okay? And if you define this expression by convention, when you apply the expected value operator, you use the density on top. It's just by definition. Okay? So this one, when you write the detail of what you mean by expected value of a ratio of log, it's going to be this whole thing, which is viewed as a random variable. And you use the density of the one on top, and that's how you define it. You don't use the one on the bottom. So by convention, you just use the density on the top for the definition. And this measure is a measure of proximity between two densities in this case. It's always going to be, that's the beauty of it, is always non-negative. And it's only equal to 0 when the density on top equals the density at the bottom. Okay? We make a fuss about the fact that it's a measure, not a measure of a distance, because if we flip the P and Q, and if I put Q on top and P down, then of course I will have to change this density also to be the Q. And it turns out in that case that this measure will be different from what we had before. Meaning that this operator, this Kullback-Leibel divergence, is not symmetric. And one of the properties of distances is that if you measure a distance between two things, it doesn't matter which one you start with, you get the same distance. So that's why we make a big fuss about this is a measure, and when you flip it, It's not going to be the same quantity, okay? So it's always non-negative. It equals 0 when at almost all points this function or this functional equal to this function. Okay? Yes?
So here, whether we use the P or the Q, this part is application dependent, correct?
Yeah.
Whether we use the P or the Q on top.
Oh, whether we use, yeah, so that
Yeah,
depends on
what we
application,
want.
exactly what you want. That's a very good question, yes, yes. And we'll highlight it with that example that I asked you to look at. I don't know if, so we'll walk through that example again. Just make sure that we're all comfortable with it. Absolutely. So let's see what else I have here. So before I jump to something else, let me just stop here and look at our reference book. And so here is the reference book. And we have the two differences here. This is KL, Q over P over Q, and this is Q over P. In this case, it says, let's assume that P is given, okay? Which is like in our case will be the desire. And when the Q, let's assume it's the output of this mapping that we have. Output of this mapping, or it could be more complicated neural network, which is in a form of softmax probability density, right? So we can change this Q. And we want to have the Q that approximates this P. So P is given the target, the blue one. In this case, P is selected to be the target. The unfortunate thing is that most libraries right now, they use P as the output and Q as the target. Here, they're using it the other way around. So keep that in mind. So in blue here is the target, it is fixed. And you have a generator, a system generator that generates Q, and you'd like to make this Q to approximate this fixed P. So we're saying, if you have the Q in the bottom, that means this guy is going to use the density of P, right? So when you look at the expression, the density of P is going to be there, okay? When you have the integral P, negative log of P, and then the integral of P, negative log of Q, right? So in that case, in the expression, in this expression, P is going to be always whatever it is, non-zero. So if P is non-zero, you're going to have, is going to contribute to this quantity. So therefore, Q has to accommodate all non-zero P. And therefore, your best estimate here that you get, closest to the minimum, will be when Q, everywhere that P is not zero, Q will be non-zero. So Q try to please all these, in this case, two-modal representation of the density. The density is not unimodal. Okay? And this other option, when you have Q on top, and therefore using the density of Q, it's your choice. Use whatever Q you want. Here is saying, okay, I found one hump or one mode. I'm going to choose Q to approximate this one mode. And because I'm using any Q, I can set Q to be zero everywhere that you have another mode. That is going to be a good approximation. Okay, so that's the distinction. You see the picture here, if you go back to where, I hope we could see the, so here they exactly show you which density you use. And I just show you the expression. Well, they're suppressing it, so I think I'm going to go back to my equations. So I want you to always think of this expression. So when you have this expression in this integral, you have this guy here. If this guy is given to you and it has multimodals, you cannot control this. Always, every time this is non-zero, okay, you have to have some value of q to try to minimize it. But if you flip it, then this will be a q. You select it. It's your approximation. When you avoid the one modal things you're dealing with, you can set it to 0. So you say, I'm going to give you the minimum, okay, by focusing only on one modal scenario. So that is an intuitive explanation of what you see here, okay? So this one here, when you put Q on top, you're going to use the density of Q. You choose the Q. So you found one modal things, you're going to do your best to approximate this modal, and you're setting Q outside of this mode to 0, you will achieve minimum, the lowest level. This one here, by definition, you're using the density of P, which means it's going to be there. It's going to always be non-zero. Everywhere that P is non-zero, Q has to give an estimate. So therefore, Q has to satisfy this mode, has to satisfy this other mode. So in this case, try to satisfy many masters, and it gets the best value that gives you the minimum, because both of these scenarios, you're trying to achieve an estimate which makes the measure close to 0. Close to 0. So you cannot achieve 0 here, but you get the one that's closest to 0. That's the best you can do. And everywhere P is non-zero, you have to have a say. You have to say, here's my Q that estimates that. And because you want to estimate this one simultaneously with the other one, you end up not satisfying anybody. You get the mean. So you get another one modal that satisfies all of them. To the extent possible, the best you can do. This one here, because you're defining Q, you can set Q outside of the single mode you found to 0. You don't worry about the other guys. The contribution to the measure is going to be 0. And you do your best to get the best approximation of this one. You focus all your energy in just replicating this one. If you replicate this mode and you have everything is 0, your minimum will be 0. Your measure will be 0 because you're guided by a measure. Okay? You're shooting the minimum. Is this point clear? Yes.
In the second case, is that Q unique or it can be on the other side?
It's not unique. It depends on where the process takes you. Because all the measure knows, just you want to settle at some minimum. Get the minimum. So here in this case, in this scenario, you can achieve the measure equal to 0. Because you latch on 1. If you latch on 1 and you satisfy it, you set everything outside of that to 0, you get 0. But you're missing out on other modes. And which one you get? Very good point. If I have a process, I initialize it, I could be having this mode or this mode. And if I have more modes, some of these modes. So this measure, which is referred to as, in my last notes, and it's also here referred to as the reverse KLD. Reverse KLD, this one here, is what you do if you have data multimodal and you use the reverse. You're going to get the best approximation of one of these modes. One of these modes. So at least if I get one of good modes, I may have another network initialized differently. I can get other modes, right? I can maybe sequentially or parallel, I try to get as many modes of my data as possible. So that's a key point that you should keep in mind. Okay, if you have this one, which is the forward, we named it, and the book also names it forward KLD, it's going to give you the mean of all possible modes. If you have multi-modes, it's going to give you an approximation which is a single mode. Yes, go ahead.
So in the case where we decide Q, are we iterating through all of the modes, or we're just after we focus on that one? Are we? Because what conclusion is made about the rest of the the modes if we just focus on this one?
Well, I mean, this one here, if you have multi-modes and you're trying to minimize this measure, we haven't really got into other procedures of how to apply a neural network to this process, right? We're just saying this scenario, this measure will be minimized if you latch on to one of the modes, any one of the modes, and focus on having a good proximity to that one mode and setting your Q outside of that mode to 0. You'll achieve the minimum. Now, noting this problem, if I have multi-modes of my data, I have to be aware that I have to do something else to make sure I capture as many modes of my data as possible. We're not discussing that right now. We're just looking at the simplest possible case and where this measure takes us. So the measure is just, if you use the reverse, you're focusing on one of the modes, okay? Whatever your process take you, okay, and you do a perfect approximation of that single mode. If you do the forward, it's gonna react to all the modes, but it's gonna give you a poor approximation, which is a single mode. Okay? We're talking about the simplest possible way. This may suggest ideas of how to proceed in a realistic scenario, okay, depending on the data and what are the avenues and what the procedures. Okay, so that's the concepts that we're using and the measure and how this measure comes in. And later on, we're going to make some things about how you could use it in your multi-layer neural network. Okay. Another thing, and instead of having comparison between the joint density of the vector vis-a-vis the product of the marginal densities, okay, you say, I'm going to make a comparison between the product of the marginal, okay, which is going to be end up this expression, vis-a-vis a process which has the max uncertainty, which is the max entropy. So if I have a random variable, and the random variable that has the Gaussian density turns out to be the one that has the maximum entropy, the maximum uncertainty. That's why we have the Gaussian density, normal density engineering everywhere. That's when you assume that, you don't know something or noise is Gaussian. So it has the maximum uncertainty, okay, for continuous random variables. Okay, so that's the maximum. That's the maximum uncertainty. Okay, and we have the marginals, and obviously you want to look at the marginals and you're trying to find the densities associated with the marginals. And you want to make sure that the marginal densities and their product is going to be as far as possible from this maximum entropy. Okay? So a sidebar here, if y happens to be a Gaussian process, has a Gaussian density, random variable, then we know exactly what the Gaussian density is, the expression of it. It only depends on the mean and the variance. These are the only things it depends on. And I have the expression, and I can apply the entropy to this Gaussian. And if I compute it, and I'm applying it to a process that has is fixed mean and variance, is going to be a constant. And and this constant will be has the exact expression that depends on the mean, obviously the dimension. We assume the variable y is a dimension m, and it depends on the variance matrix, determinant of the variance matrix. So this expression, it's a standard. You can look at the Gaussian, look at the contribution. You can actually compute it easily because the Gaussian density depends on only two things: the mean and the variance. It doesn't depend. This doesn't have any higher order statistics. And we have the exact expression for it. We can apply the definition of entropy to it. And we just do the calculations, and we're going to get a constant that depends on the mean and the variance. And this constant will be the largest value for entropy because it has the largest uncertainty. Any other density will have less than this number, cannot exceed it. So another measure is to make sure that the marginal density, which is on this side, you want to have a process where the process is the max from the Gaussian. So you are, in fact, the output, you want to minimize uncertainty. You want to minimize the total entropy or the mutual information. Okay? So you have one which is max, and you have these marginals. So all we've done here, we're saying we're going to optimize non-Gaussianity. We want the output here, okay, is far away from being Gaussian. So this thing is the difference between our output, that we can manipulate its density, and this ideal Gaussian that has the maximum uncertainty. We want to keep it as far from being Gaussian as possible. Now, if you want to make it as far from being Gaussian as possible, you can either go in something called sub-Gaussian or sub-Gaussian. These are potential directions, okay? So typically, because of the nature of the definition of entropy and information, because it uses the natural log, typically this ends up going towards the sub-Gaussian or exponential type, okay? Sub-Gaussian would be Laplacian, exponential, anything that has an exponential form where it peaks near the origin and goes down. So right now we have a measure which is a measure of optimizing non-Gaussianity, meaning that our output is going to be far away from being Gaussian, because being Gaussian is the maximum uncertainty, maximum entropy. So we want to make our signal coming away from that maximum uncertainty. So in other words, this term here that used to be coming from the actual joint entropy of the signal, we're going to replace it by an expression which is the entropy of a Gaussian process. And therefore it becomes constant, okay? And then we're only going to optimize based on the other stuff. When you have optimize, you either maximize or minimize. If you have a signal, you want to minimize it. If you want to maximize it, you can take the negative of that. Therefore, you minimize that. So you have a signal. Your goal is to maximize it. You put a negative sign to it, then your goal becomes to minimize it, so on. So therefore, we can talk about minimization, making sure that we're going to insert whatever negative sign we may need. Okay? So the point of this second approach is that instead of dealing with two terms that relate to the actual output that are coming out, one of these terms is going to be fixed as constant. And every time you have a constant in a measure and you're trying to optimize, that constant plays no role, because this you're going to optimize based on things that relates to this marginal signal. Okay? So this mutual information becomes really just trying to optimize this expression, and this expression only relates to the marginal of the signal. So you don't have to deal with the joint density. You just deal with marginal densities of each one. So let me I think there is also something here, I believe. Assuming you read it, but I need to share that so we can. It talks about, I think, various probability densities, I believe. Somewhere. So here, so you have all these different distributions. So eventually we'll be interested in the Laplacian distribution or exponential distribution, but pretty much we're going to be interested in this distribution. So we know that Gaussian is proportional to an exponential, and here you have, for example, in the scalar case, x minus the mean, this whole thing squared. So instead of square, you're taking power 1. So that's what makes the Laplacian distribution of a signal. And this Laplacian distribution or density is associated with signals such as speech signals, often referred to as having Laplacian densities or distributions. And this is also has an exponential form. So these are the family of exponentials. And if you plot this one here vis-a-vis, I don't think they have the plot vis-a-vis the Laplacian, you're going to end up with something that peaks at the origin, okay, and then dies out. It has a heavy tail, so that means it's gonna slowly die out compared at far away. So often in statistics, we use the Gaussian distribution as a reference for all other distributions, and we can have comparisons between other distributions and the Gaussian. And there are a lot of expansions of other distributions with reference to the Gaussian. So it's like when you have Taylor expansion for generic function, you can have also distributions of, expansions of densities with reference to the Gaussian distribution. I think they're not making distinction between distribution and density. I think what they mean is really densities. Distributions often referred to when you deal discrete variables. But I think we are really looking at densities. Okay. So this is the form. So this Laplacian and the exponential are special classes of the sub-Gaussian. Sub-Gaussian, if you have this variable, random variable, just view it right now as a scalar, minus the mean over the variance, right? So, and if you have this difference, and then this is to the power. If this is to the power 2, that becomes Gaussian, normal distribution. If the power less than 2, then becomes sub-Gaussian. If the power is more than 2, then becomes sub-Gaussian, in a way. Okay, so that it's centered around the Gaussian, okay? So let's see what we're going with this. So we have expressions for each one of these marginals, okay? We're gonna focus on the scalar, one component at a time. The entropy is defined to me the expected value of the information. And that's the expression for it. And if you have an output and you have a signal S like we started with, then you map it, then you have an output. And then you want to tweak that transformation to make this output has certain statistics, right? By way of a transformation, because your transformation is going to be adapted, it's going to be changed. Every time you change it, you're going to change the characteristics of the output signal, and therefore you want to control it, so you want to make it a certain random variable statistics. But you don't have any expression for that. So one way is to and you need it for the computation. When you look at the minimization at some point you're going to say, I need some information, an expression, to do the computation of this density. So typically we can focus on, is the signal that I want output there sup Gaussian or sub Gaussian? These are two rough categories of things. So you want to go away from Gaussian and sup or sub Gaussian. And so if you assume that this one here, density, is, let's say, of a sup Gaussian, then it's going to have proportional to an expression, exponential, with negative some constant. If this is zero mean, you don't have to subtract anything, and really what's key here would be the power. So if this power gamma equals to 2, this is the expression for Gaussian, which is the reference. If this gamma is less than 2, then this exponential expression renders the density sup Gaussian, which means it's going to have a peak at the origin, and it's going to be a heavy tail that dominates the Gaussian distribution. So note that we're focusing on the distribution itself because our network or our transformation is going to be adapted and changed, and we're interested in what we're going to be outputted there. And we're not interested in the actual values that come out. We're interested in their densities because that's what we're seeking to modify. So here, this is the Gaussian, this is non-Gaussian, and if this alpha here is just a parameter which captures 1 over sigma or sigma squared. So this, we just say, let's have one parameter for it. And when you have the natural log of this probability, this whole expression, which we define it to be the information with the negative sign, you apply the natural log of this one, this exponential goes away, you look at the exponent, that's step 1. And 2, with the negative sign, you're going to cancel this negative sign. So the information is really the exponent, which is the alpha times the absolute value of yj. Note in this case, we can also select this gamma equals 1, which is the definition of Laplacian, which is the density associated frequently with speech signals. So this is Laplacian density is going to generate for us expression for the information that is really this expression. And this expression, when you plot it, the absolute value as a function of yi, this picture is not coming out nicely here. So let's see if that something is. Yeah, here it is. So I don't know, for some reason disappeared. So all we've done here is just take this one mathematically. This one is going to be a piecewise linear function, this forward, and this alpha really serves as the slope. So we're just putting what this expression is, and this is the exponent of the density. So the information expression, not the mean information. We always think that there's an expected value operator applied to this one. But the entropy or the information is expressed like this function, piecewise function for Laplacian. So this expression for each one of those, the entropies, I know that I have this expected value always there. For computation, we can mimic the contribution of the expected value by having a time average, assuming that this process is ergodic or we have enough means to approximate it. So that's why we're dropping this expected value. In some cases, you may want to actually do the computation of the expected value. You have a full-fledged computation of this expression. So eventually, if the entropy is going to be our guidance, our measure, it's going to be serving as a loss function of something. So I'm looking at one stage transformation, and if I use the loss function, which is the entropy, and I'm going to optimize it in this case, anytime I do optimization, I have to apply the derivative, the gradient. So because the entropy is going to be equivalent to this quantity, this one is equivalent to this quantity. There's some constants, scaling, which doesn't really play any role in the optimization. I want to see what is the partial derivative of this entropy, which is equivalent to this quantity, with respect to yi, which is this one here, which is going to be the derivative of this one here, which is, in this case, the derivative is going to be really the slope alpha, and then it's going to be the sine of this y. So really the derivative is going to be the sine of the y. This is the derivative of this function. So pictorially, the derivative of this one is going to be a flat line like this at height alpha, and then it jumps to negative alpha, just a square or a step function, right? That's the derivative, which is represented by this sign. So we're going through elaborate stuff here, and I hope so this is the derivative that we have, because when I apply optimization, I'm applying gradient descent. That's how I'm going to steer my system towards a better parameter. Remember this transformation that we're going to have. We're going to make it, that's what we're doing, make it an adaptive. And this adaptation is going to minimize an expression, which is the entropy. All right? And when I took the derivative, I have this derivative will be something like this. And this derivative is fine, except it has this jump. Okay? And to avoid this jump, you want to approximate, as it is done in practice, by something smoother. And a good choice, one choice, will be using the hyperbolic tangent nonlinearity. And now you notice the hyperbolic tangent nonlinearity shows up in many of these neuron nonlinearities. Okay? So the derivative here could be approximated by a smoother thing to avoid any instabilities or thing is getting stuck. So if this derivative is like that, then we can rewrite a smoother version for the soup Gaussian as proportional to exponential of minus alpha. And this expression, which is the integral, is going to be really approximating a soup Gaussian. Sorry here. So a lot of footwork here and getting expressions of all these things just based on some mathematical expressions. It's not important. What's important is we don't have an expression for the density for the process. Okay? We're going to force the density to become soup Gaussian of this form, and in this soup Gaussian, if we make it Laplacian, and we're going to have an expression for this entropy that is the absolute value of y sub I, which is the variable, to a power alpha, which could be 1 or less than anything that's less than 2. Typically, people will use 1 to say that I'm going to force the outputs to possess marginal densities that are Laplacian. Okay? So this is just saying that I can have an approximation of the density which is going to be used in my adaptation. And I'm going to seek making the densities become Laplacian. Okay? If it's not Laplacian, you can have any gamma and you make it some sub-Gaussian. Okay? So that's step one. Step three, how can we do this process adaptively? So I have an input signal, I have a matrix, and generate an output. This matrix needs to be determined, and the way I'm going to determine it is that I'm going to adaptively change the matrix in order to minimize this measure. What is this measure? The uncertainty or the entropy at the outputs. And I'm going to assume that these outputs are going to be forced to be, in this case, sub-Gaussian, and specifically I'm going to make it Laplacian. Laplacian is when gamma equals 1. Okay? What is this going to get me? Well, it turns out this relates having the outputs having Laplacian densities is going to give you the outputs become sparse, meaning that you have the most amount of zero outputs in the vector. So you have a vector, okay, and only some of them that need to come out will be non-zero, the rest will be zero. So that's referred to as sparsity. So one property that we have here is that if we force the outputs, the only guidance we have, we're going to force the outputs to possess or attain density that are Laplacian. Then we're going to, point one, we're going to have sparsity, which is equivalent in this case to statistical independence. So if the marginal densities become statistically independent, far away from Gaussian, they're going to be guided towards becomes Laplacian in this case, and they will become statistically independent. And one manifestation of statistical independence that you're going to end up with sparsity, meaning that the output vector will have the maximum number of zeros in it. So only some signals will be firing or outputting things that is not zero. You have the most number of zeros. So that is forcing sparsity on this output. When you make the transformation, I'm guiding the adaptation of the weights to the point that's going to minimize the uncertainty at the output, okay? And it turns out when I do that, I'm going to have statistical independence between the signals, okay? And statistical independence is going to manifest itself by having the maximum number of zeros in this vector. So what do you mean by statistical independence? That means these outputs coming out, they're not going to be related to one another. You don't have signal the same source affecting all of them. So when they're firing, they're not related to the other guy. So when I'm firing, it doesn't mean the other one is going to fire. Because if the other one fires when I fire, that means there is a correlation between us. So we're saying this is the one that doesn't have correlation. It has stronger than correlation. It has independence. Okay? So there is the statistical aspect, which saying that the output will be statistically independent, and there it becomes sub-Gaussian. And there's the practical contribution here that this also means for us, when I have the output vector, I'll have the maximum number of zeros. Not all of them are going to fire. Only the minimum ones that need to output something, which is like view each one is going to capture some feature. So if you have a feature, it's not going to show up in this signal and this signal. It's going to show up either in this signal or that signal, not all of them. So that's where the concept of sparsity and statistical independence of output are very important in this case, right? Because it's going to give you the minimum representation, non-zero representation. So you have a vector, 100-dimensional vector. You only have 4 elements that are outputting for that feature. and then another 4 elements for other features, and so on. You don't have the all 8 elements respond to both features. Because if that's the case, then they're correlated. They're not statistically independent. So it's like, and also that relates to having the maximum number of 0, which is sparsity. You have as many zeros as possible. You only have non-zero values when you need to, when there's some feature that these neurons or these outputs are capturing and not the other ones. And you don't have multiple neurons responding to the same feature. You have only neurons correspond to one feature, other neurons to other features, and so on and so forth. So it really is statistical independence among the output carries over into a practical meaning, which is sparsity. Okay? And it relates in this case to having an information that's captured by the L1, because the absolute value of the signal represents an L1 norm of some sort, okay, of all the signals. And the next thing is say, why would we want to do that? Why do I want the outputs to be statistically independent? That's not our game, right? Our goal is to have the output represents some density, right? This will apply, the statistical independence applies mostly to intermediate layers. Because remember, like in the neural network, we have multi-layers, and we only put restrictions on the final output to be equal to something. We don't care, we don't say anything about the intermediate layers. We just say intermediate layers will try to help this output reach this thing here. It turns out there are a lot of different options. There's an overfitting. These intermediate layers could be in this position or that position. In both cases, they satisfy what the final layer wants. So this additional constraint on intermediate layers saying, no, intermediate layers, I want to restrict intermediate layers to be statistically independent. Meaning when I move from the input stage to any intermediate stage, I only carry non-zero outputs that are meaningful for every stage. And therefore, by imposing statistically independent on intermediate layers, you have, when you do the training, it's most likely you have a repeated structure. You end up with less possibilities of the weights, restricting the selection or the search space of the weights. So the calculations here apply to a generic layer in a single layer, and you're saying I want to have statistical independence among the outputs of these layers Y1, and it turns out this statistical independence, in this case, when we have Laplacian distribution imposed, is going to be equivalent to having sparsity, okay? And then the next thing is this is going to be applied to any intermediate layers to restrict all possible search for parameters to satisfy the guidance at the output layer. So this mathematics applies to a generic layer, and the calculations are straightforward, set as gradient descent of a measure, and this measure is mutual information, and you just apply the gradient with respect to this weight that you have, and every weight at a time. And the trick here is that you use the Kullback-Liberal divergence between one option between the joint and the marginal. That's one approach. And the other approach, we said we totally neglect the joint because we set it to be the maximum, and we just focus on minimizing this one here. Once I have the expression, the loss function, the calculations has nothing to do with statistics, becomes mathematical optimization, and you crank the computation. There's some steps here from statistics that because in this one layer I'm mapping my x is mapping to y through a w, we go back to statistics, say if I have a density given on X, which is my input data, how we transfer that density to Y if I have a transformation. So I have a random variable, I map it to a Y by a W. And statistics tells us the density, the joint density of X is going to relate, you're going to create a joint density of Y by dividing by the determinant of this matrix transformation. This is just from statistics, probability. If X has a probability density, the resulting density of Y, the transformation, is going to render Y having this density, dividing it by the determinant, absolute value of determinant of the matrix. This is borrowed from probability. Okay? Once you have an expression like this, you can take this measure and do the math by replacing every time you need a py of y, you replace it by this quantity. So this y of y, which is the entropy is defined this way, but this natural log of y, you take this expression, you plug it in here, you write it in this fashion, and then your measure that you started with, you replace entropy of y by the entropy of x, and this natural log of the absolute value determinant of w. And now you have an expression, and you want to optimize this expression with respect to this parameter to the w. So you just crank out the gradient. The continuous form or the component wise, you write it this way. And if you calculate this one, and you can either try it or look it up easily, you're going to get an expression after the calculus which requires the derivative with respect to these two terms. This guy doesn't depend on w, so derivative is going to be 0. This one you need to compute, and this one here, the marginals. So the calculations are documented. So you have to go back to matrices, determinant of a matrix. So this is determinant of a matrix, a natural log, and you want to take partial derivative with respect to w, and determinant by definition, you can represent it as each component. You scan either row or column, and you write the cofactor ij, the cofactor of this one here, and I'm delegating the details of this one here. Bottom line, this quantity derivative, it's going to end up with the same matrix inverse transpose, so for whatever component, the component of that matrix. I'm going to delegate this one. You can either look it up, and I can give you a resource when you look it up. It's calculus, okay? But that's what this term is going to give you when you do computations. And then this summation, the other terms, the marginal with respect to the weights, you walk through the chain rule of this expression with respect to yi with respect to weights. And this one, the yi with respect to the weights wij is going to give us yxj. And this expression, when we compute the derivative, is going to give us some function. Okay? This function should be a function, and this function, which is a vector function of each of the marginals, and then each one of those functions is going to be the partial of the entropy with respect to yi, this expression. And this is this term where you need information about the density. And we're going to use the Gaussian approximation of this density. And depending on the estimation of the density of the process, Gaussian or sub-Gaussian, you do the calculations, you end up with an expression of this sort. Bottom line, you can actually calculate an update law for the parameters that will serve to render the output having that density, okay? And also the output becomes statistically independent. So the calculations are really straightforward, but basic calculus that you have to know this expression. So this expression, the natural log of py, is replaced by alpha absolute value of y. I get one form of this nonlinearity. Okay. So it turns out in the update law, you need this function f, and this function f will depend on your knowledge or assumption over the type of densities that you're seeking. And if we set the density to be exponential or Laplacian, then we can have an expression here in the update law. If we don't, then you can have a generic expression here that steers the output to possess either Gaussian or sub-Gaussian general forms. Okay? And there are techniques where, as you update, you can estimate information about this outputs itself and change this nonlinear function. So there's another thing on just flash is there's a gradient and there's natural gradient. And the natural gradient applies when you are updating matrices, and it relates. So if this were the gradient that we just apply the calculation, you need a factor here, which is the weight transpose weight multiplied to make this one into a natural gradient. So if you do all the calculations, bottom line, you're going to get an expression of this sort. That you're going to have the update is going to be an identity minus an outer product between a vector, nonlinear vector, and y transpose, which is going to be a matrix, times this matrix. So I'm suppressing the calculus. I'm showing you the steps and the results. I can refer you to a specific place where you can look at the very nitty-gritty details, not very difficult, but all the guidance on how to get these expressions are here. And this is one form of having this update law and interpretation of this update law saying the change of weight is going to have the difference between the identity matrix and a covariance matrix that uses nonlinearity, okay? And then times this weight. That's the update. So if you keep updating, you initialize this one from some random weight, and you keep updating this weight will be going towards a final weight with the objective making the outputs having sparsity or having statistical independence. Okay? So you don't have any reference. The reference is obtained from the concept of the densities of the outputs, which are sub-Gaussian in this case, will be statistically independent. Okay? So bottom line, this is the form of expression. And if this f happens to be linear, meaning instead of f you just have this one y, in that case, is equivalent to assuming that the densities are Gaussian. And this one becomes the correlation matrix. And this becomes a PCA application. So to move from independent components to PCA, you just make this nonlinearity linear, and this becomes a covariance matrix or outer product of this vector with itself. And the key thing to make it independent, to select this f function, and this concept of making sure this f function comes from a Laplacian density is saying that I want the outputs not to be Gaussian, far away from Gaussian, sub-Gaussian, and specifically Laplacian. Okay? So these are the computation. Typically, in our libraries, we don't see much usage of these. In the example that we see, often you don't put any intermediate restrictions that are explicit in the libraries on intermediate layers. So if you notice, in the convolutional network feed-forward networks, we have some operations, we have some randomness that's generated in these steps by the dropout or what have you, to create some randomness. But the only guidance is really the loss function applies to the final layer. And in that process, if somebody else comes and reinitialize things differently from what the library does, or you select different seeds, you want to get different results, and you're going to get different weights and parameters. And they will approximate the final goal with different degrees. Some of them will succeed, some of them may not succeed. So the concept of saying that let's focus on the intermediate layers and put restrictions so that every layer captures essential information from the previous layer, and this information, every output, is not going to replicate information from other outputs. So they become statistically independent, which is more than decorrelated. So each output will focus on information to the next layer that is unique from the other outputs. So you don't have redundancy in the outputs. So in this process, that could, in conceptually speaking, lead to a performance that could be faster and avoids things getting stuck or unexpectedly fail, because we have libraries and we have tutorials and examples which have been optimized, and they have initialization, internal initialization that's been optimized, and they give you some default parameters that have been selected for you, okay? It doesn't mean that if you come with another problem, another data set, that this parameter set will work well for those cases. And, so instead of repeating things from scratch, sometimes making sure that transformation is efficient from one layer to the other, okay, is one way of efficiency, is making sure that every layer produces sparse outputs, which means the outputs will be non-zero if there's a meaningful information carried over. If there's no meaningful feature, you just set the rest to zero. So you have fewer parameters setting information to the next one. So and this could be something in obviously unexplored. Example in our case is very helpful in making sure you don't get stuck in unexpected domains. So anybody who wants the details of those things, I'll be very happy to share those details, or the reference. We have our book here, which may or may not have these details. And I have also in the syllabus, I have another book reference that will have these details. I have two references. One of them is our book, and I have another reference just for further technical information. And this course, by the way, the 885 course, is different from the other course that I teach in the fall. This includes some theoretical aspects that we have to gain some things beyond the libraries, okay? Because you're envisioning things beyond what the status is in the libraries right now. So if you compare PCA and ICA, is one way of looking at it is that the presence of this nonlinear function of the random variable. So in PCA, you have linear function because that comes from a Gaussian. In PCA, if you notice in the example I've shown you, we always draw things in ellipsoidal shape. And the ellipsoidal shape denotes that the statistics are really coming from a Gaussian shape. Okay? So the key thing is having nonlinearity, and the presence of nonlinearity depends on the family of densities you want your outputs to possess. And we're saying we're going to have a soup Gaussian, which means in this particular case, we selected the Laplacian. The output is going to be forced to be Laplacian, and they're going to be statistically independent. Okay, so if your data comes from a Laplacian source, often it has sparsity, meaning that most of the outputs will be zero and only a few outputs will fire when there is relevant information. So I'm having here a sidebar that's saying if you compare this one, the Laplacian, the PCA, and this is we don't cover this one, the adaptive PCA this year. We only talk about the algebraic PCA. We do things offline. We do it as a pre-processing step. But just to let you know, you can create the same mapping that we have here, and you say, I want this weight to follow or be updated by this update law. And this update law, which is similar to this one here, except here you're dealing with Y and Y transpose, one known for adaptive PCA. We're not covering it. I'm just flashing this one here. In the reference, you can look up adaptive PCA, but it's less of use right now because in most libraries you could do this PCA non-adaptive, and you could do it by procedure that we follow by having the covariance and looking at the eigenvectors. But you can find the direction of eigenvectors adaptively from the data, where the update law for the weight is going to follow something like a covariance of the input signal, covariance of the output signal, and you have the weight matrix on both like this. And here, for technical reason, you have LT, which stands for lower triangle. So you have a matrix, you just take that, you shut everything in the lower triangle to zero. Okay? And I'm just sharing what the adaptive PCA is. If you have a layer, we're not discussing it at all. We're only using algebraic PCA. So if you want some of the computation details, you can obviously look at the chapter 3 in the book that we have for the class. Here's the other reference that I also have in the syllabus, which is a textbook by Haken called Neural Networks and Learning Machines. And it's in the syllabus. And you look at chapter 10 about adaptive ICA. And that's what it covers. And also there's a chapter 8 for adaptive PCA. Okay? If we're only looking at the adaptation for ICA, and we're using it not for the final layer, we're not interested, at least in this class, we're not interested in having a network that gives us outputs that are statistically independent. In some applications, there's some interest there. For example, there's a lot of research on having, if you measure mixed signals of speeches, you want to undo the mixing and separate those speech signals. So there's a literature on that that's full by having a single layer adaptively doing that for you. So if I have 10 microphones here, and we have 10 people speaking at the same time, each one of these microphones will pick up mixed signals which is called mixers of all these 10 speakers. And then the machine has to sort and separate those speeches. And some of the techniques is using ICA, independent component analysis, by viewing those speeches coming from independent sources as independent signals, and speeches often have Laplacian signals, and people have applied that in separating the speeches. So the machines separate John's speech from another person, another person, another person. So a lot of success stories there in having the single layer adaptive neural network that performs signal separation using ICA related techniques. But in our purpose here, we're viewing as applied to a layer, and our purpose we have intermediate layer, and you want to have the intermediate layer having a sparse representation or statistical independence. And I hope I convince you by now there's value in having statistical independence by making sure the outputs produce non-zero value if there's some features, and not all of them produce non-zero. Only fewer ones relate to some feature because they're statistically independent. So what happens is that each output will select some features different from the other outputs and be responsible for those. Okay, we stop at this point, and if you have any questions, let me know. And I think this is the handout that we have for today.